So as a review, because we're leading up towards the mole, which is going to be a super important concept, and it's going to kick off again. We've kind of taken a little bit of a break from unit conversions and unit analysis, but that's definitely going to come back, and then we're going to continue to do that for the rest of the semester. So actually, let me go even farther back than this, and we'll just kind of go through this real quickly. But had kind of asked the question, like, how much salt, sodium chloride, can you consume before you go over the USDA or the FDA's recommended limit of 2,400 milligrams? And this question is a little bit tricky because salt, table salt, is not just sodium, which is what the FDA is recommending that you have less than 2,400 milligrams of, but it's sodium chloride. And so the sodium and the chlorine, I mentioned this last week too, have different masses. So we're talking about individual little building blocks. And actually, I brought some of these examples here, which we'll go over later. But even looking at the periodic table, the number at the bottom of each of the elements is the atomic mass. All right, so that's how heavy an individual atom is, essentially. So sodium's only 22.98, or 99 if you round, and then chlorine is 35. So we can't just look at the formula of sodium chloride and say, oh, it's 50-50 sodium and chlorine. Right? One is heavier than the other. So this is important in a lot of places, not just trying to figure out how many potato chips you can eat. But in things like mining, you're looking at collecting raw ore, which is not all iron. There's a lot of other stuff in there. And so how much of it is actually iron? Or in terms of protecting the ozone layer, compounds like Freon have chlorine in them, but they're also made up of carbon and hydrogen, and it's only the chlorine in there that we're worried about. So we did some examples last week, and using this analogy of nails by the pound. So instead of counting individual nails at the hardware store, they just put them in a box and they weigh them and they say, oh, this is 1 pound of nails, or 2 pounds of nails, or 1.5 pounds of nails. And then using the mass of an individual nail, or how many nails, or how much 12 nails weighs, a dozen, we can figure out how many nails are in the container. So we had this example of 2.6 pounds of medium-sized nails, weighed 0.15 pounds. And we were able to calculate, and this is the new format that we're going to start using for our unit conversions. We were able to calculate that 2.60 pounds of nails is 208 nails. So we can do the same thing with atoms. And I did this math here real quick, but for atoms, there's no way that we can actually count them individually because they are so tiny. And I did this math that if you counted atoms every single day, 24/7, for 83 years, you would be able to count, 2.62 times 10, 1.31 times 10 to the 10 atoms. And that is 10 times 10, 10 raised to the 10 times less than there are atoms in a single mole. So in 1 gram, or 1 mole of carbon, this is charcoal, this is all carbon, this is 12 grams of carbon. So you could count not 1/10 of this, not 1/100th of this, but 1/1,000,000,000 of 1/1,000,000,000 of this. Or actually 1/1,000,000,000 of this, less than that even. So the teeny, teeny, tiniest if you tried to count them one at a time. And so the unit that we use for this is the mole. And this is where we're starting to get into new content. And the mole is a really, really, really large number because we need a large number to be able to count these really, really small atoms. It's also called the chemist's dozen. And even though it's not a huge abbreviation, we do abbreviate mole, M-O-L-E, as MOL. So 1 mole is equal to 6.022 times 10 to the 23 of something. So this is like saying a dozen, right? You can have a dozen eggs, that means 12 eggs. You can have a dozen nails, that's 12 nails. you'd have a dozen donuts. I wish I had a dozen donuts right now, but right, a dozen is 12 no matter what you're counting. So same thing applies here, except now it's not just 12, it's 6.022 times 10 to the 23, which is an insanely large number. And that was Amadeo Avogadro came up with this number. And it's convenient because it makes up quantities that are tangible, that are easy to work with. So 1 mole of copper atoms would be 22 pennies. 1 mole of helium atoms is about 2 balloons of helium. Right? So instead of having these insanely small things or going too large, it kind of makes them more relatable. So like I showed you, this is 1 mole of carbon, right? So that's a manageable amount of carbon. This is 1 mole of copper. And then something like this. This is 1 mole of nickel chloride, which takes up a lot more space than your copper. And the mole is important because we have to count individual atoms because they have different masses, and then we'll use those masses, tie that to the mole. The mole was calculated actually based on 12 grams of pure carbon-12. So something not unlike this charcoal, right? So this is 1 mole. This is 6.022 times 10 to the 23 atoms of carbon. And by using that, that's what makes everything sort of at a human-sized scale. And it also establishes a relationship between the mass, or the grams of carbon, and the number of atoms in that mass. So that 6.022 times 10 to the 23 atoms is 12 grams of carbon. So now instead of saying, instead of having to count atoms individually or even having to add up the masses of individual atoms, we can just say 1 mole, and know that we're talking about a large quantity of atoms. Just like we don't have to weigh out or count out 208 nails, we can get the mass or the weight of those nails and relate that to how many nails there are going to be. So this is going to be a conversion factor that you can use like any of the other conversion factors that we've talked about. And just like 1 dozen equals 12 nails, 1 mole equals 6.022 times 10 to the 23 atoms if you're talking about atoms. And actually, if you had, I guess to try and give you a little more perspective, if you had 6.022 times 10 to the 23 marbles, they would cover the entire Earth to a depth of 6 feet. So for atoms, it's a very fine number. For marbles, you don't want to use this because there haven't been that many marbles made ever. And probably never will be. So if we want to convert 9.5 times 10 to the 27 atoms to moles, start out with that number, 9.5 times 10 to the 27 atoms. And we're going to start using this grid. So how does our conversion factor fit into this? How do we convert it from atoms to?
We would have to figure out how many atoms are in 1 mole.
Yep, so 1 mole is 6.02 times 10 to the 23.
So we would put that 6.022 on the top and then 1 mole on.
Yeah. Oh, wait. Sorry, no, flip it.
Okay, yeah. I always get them like mixed up, like the top and the bottom,
Yeah, so you want to have,
so they cancel out.
right. So you put what you want to get rid of on the bottom, and what you want to replace it with on top. Yeah, and 1 mole on top. And then for this conversion, then we just calculate it. get out my calculator. So 9.5 times 10 to the 27 divided by 6.022, 10 to the 23. So this is 1.5775 times 10 to the 4 moles. So accounting for significant figures, here we'd only have 2, 1.6 times 10 to the 4 moles. So again, this is why I hammered so hard on unit conversions up front. This works exactly the same as those did, so if you have to go back and review unit conversions, definitely go back and do that. All right, so if we wanted to count atoms of gold, so how many atoms of gold are in a pure gold ring containing 8.83 times 10 to the negative 2 moles? So 8.83 times 10 to the negative 2 moles of gold. And our conversion factor is still going to be 1 mole equals 6.022 times 10 to the 23. So if we're talking about moles and atoms, right, 1 mole is always going to be 6.022 times 10 to the 23 of anything, right? We can have that many marbles. Well, there's probably not enough glass in the world to make that many marbles, but if there was, you could have that many marbles. Or you can have that many atoms of gold or silver, copper, right? It can be of anything. So how would we set up this conversion factor? Yeah, so moles on the bottom this time because we're starting with moles. So 8.83 times 10 to the negative 2. Sorry. 1 mole of gold. And then 6.022 times 10 to the 23 atoms of gold. Need to drink more of this coffee. Right, and so we can replace, or we can add, it can be moles of gold. We have to be using that consistently. So we're starting with gold, we're talking moles of gold to atoms of gold. So then these units will cancel out. 8.83 e to the negative 2 times 6.022 e to the 23. So 5.317 times 10 to the 22 atoms of gold. How many sig figs should we have? 3. 5.32 times 10 to the 22. Any questions so far? Yeah.
6.022 times 10 to the 3, that's not exact, right?
There would be more decimal places than that, yeah. But it's rounded to 6.022.
So if it was less precise than another number, that would be a least number of significant figures if it was like, say, 8.83000 or something?
Yes.
Can you go back to the last page just so I can see the answer?
Oh, yeah.
Why are these easier than conversions that we did in the beginning? Or are they going to get harder?
I would say, yeah, I would say these seem easier because now that was like, a few weeks ago. So you struggled with that, digested it, and now you understand it. So now looking at a new unit conversion, it's just a unit conversion. And so you're hopefully better prepared to learn it and go over it. yeah, and these, we're going to add, there's going to be more variations, there's going to be more things to convert, but for now we're just doing atoms and moles. We will add grams in today. Is everybody good on this slide too? Okay, so again, we can't count individual atoms. So, well, it's good to know that 1 mole is 6.022 times 10 to the 23 atoms. We can't actually use that conversion unless we already know how many moles there are, because we can't count the individual atoms. Again, it would take more than a lifetime. So the next conversion factor that we need, just like we use for nails, we use the weight of 1 dozen nails. For atoms, we use the mass of 1 mole of atoms. So we're going to use a relationship called molar mass, and it's the mass of 1 mole of atoms. And it's specific to each element. I think it was in this class I showed you guys the, I'll let you guys actually handle some of these things in lab on Wednesday. But was it for your lab that I brought up the mercury? Did you guys see that, how heavy that is? Okay, I'll show you that too. All right, so each element is gonna weigh something different. So if like I'm holding this is 12 grams of carbon. This is 1 mole, 6.022 times 10 to the 23. This is 1 mole of lead, and while they look to be roughish the same amount, this weighs a lot more. Right? This is lead on the periodic table. So this should weigh 207 grams, while this only weighs 12 grams. Could be a difference in glass. So for Avogadro's number, carbon 12 atoms, or Avogadro's number is the exact number of carbon 12 atoms and exactly 12 grams of carbon 12. So the atomic mass unit is 1/12 the mass of a carbon 12 atom. Now, the reason on the periodic table that carbon isn't exactly 12 is because, like we talked about sort of at the end of the last chapter, there are things called isotopes. And isotopes will have different numbers of neutrons. So there's carbon 13, there's carbon 14, and those abundances are reflected in the numbers that we have on the periodic table. So we don't have pure carbon 12. We have carbon 12 with about 1% of carbon 14 or carbon 13. And so just like with atoms, right, the mass of nails is going to be different for large nails versus small nails. 1 dozen large nails, well, let me ask the question. You think 1 dozen large nails is going to weigh more than 1 dozen small nails? Right? So if we have 1 mole of a heavier atom, it's going to weigh more than 1 mole of a lighter atom. So sulfur, if we had 1 mole of sulfur, it'd be 32 grams. If we have 1 mole of carbon, it's only going to be 12 grams. And we get those numbers straight from the periodic table. So the mass of 1 mole of atoms changes for different elements, and we can use these as conversion factors, right? This is the same format that we have for all of our conversion factors. Now we just have conversion factors that are specific to each type of atom. And that maybe adds some complexity, but shouldn't add too much. So lighter atoms, less mass, and molar mass is the conversion factor between grams and moles. So let's calculate it. So if we have 91.4 grams of calcium, how many moles of calcium is that? So it would be the conversion factor between grams of calcium and moles of calcium.
1 mole of calcium up top, and the bottom would be the mass, atomic mass, 40.0.
Yeah.
0.078.
So the conversion factor is 1 mole of calcium is 40.078 grams of calcium, which can also be written as 40.078 grams per mole of calcium. So yeah, we'll have 1 mole of calcium on top, and then 40.078 grams of calcium on the bottom. So grams of calcium will cancel out, and we'll be left with moles of calcium. So 91.4 divided by 40.078 is going to be 2.28 moles of calcium. Yeah. Well, it's on the periodic table. And on exams, this won't be a factor for Wednesday's exam, but on future exams where you have to calculate molar masses and stuff to get answers, just use the number that I give on that periodic table, because those are the numbers that I'll use to calculate answers. So those are the numbers I'll expect you to use. Are there any questions? Yeah.
I thought the number on the periodic table was the mass of an AMUs of an individual atom.
Yes. They're numerically the same. Yes, it is. It's by design, yeah. So, yeah, one AMU is numerically equivalent to 1 gram per mole. Yeah.
So is gram per mole assuming like a mixed amount of isotopes then?
Yes. Yeah, because unless you've gone through the very rigorous and difficult process to separate the isotopes, if you go outside and you dig in the dirt and you get a bunch of carbon, it's going to have the distribution of isotopes that's the same basically everywhere on Earth. There's some things that will affect that. In different areas, you'll get slightly different isotope compositions, but yeah, for the most part. Good questions. All right, let's try another one. So we're going to calculate the number of grams of sulfur and 2.78 moles of sulfur. So start with 2.78 moles. And then our conversion factor from moles of sulfur to grams of sulfur would be well, if we put the mass on the bottom, that's the next step. What's the conversion factor first? How many moles? So 1 mole of sulfur is how many grams? Yeah, it's on the periodic table. So, or 32.066. So we want to put we're going to put the units that we want to cancel out on the bottom. And those will be the units that match our first number here. So that'll be 1 mole on the bottom, and then 32.066 grams of sulfur on top. So 2.78 times 32.066. That's going to be 89.14348. And then the correct number of sig figs here would be 3. So 89.1 grams of sulfur. So different element, different conversion factor. They all come from the same place, right? They're all off the periodic table. You always have a periodic table available. Still good? Okay. How many carbon atoms are in a 0.58 gram diamond? Who knows what diamonds are made of? Carbon. Yeah, diamonds are actually the crystal form of carbon. So you can take the graphite or the carbon that I have here, and if you squeeze it together with enough heat and enough pressure, you can make it into a diamond. There's actually a way with 2 coffee cups that you can do that in a microwave. Very, very, very teeny tiny diamonds. So how would I start this problem? Mm-hmm. 0.58 grams of carbon, because that's what diamonds are made of. And then what is the conversion factor? So how many? Yep, 12.011. So yeah, 12.011 goes on the bottom. 1 mole carbon on top. And then 0.58. And so, again, this is the same format as writing it out as 0.58 grams of carbon times 1 mole. Just to make sure we're all on the same page on that. So we're multiplying everything on the top and we're dividing by everything on the bottom. So 0.58 divided by 0.011 is going to be 0.048289 moles of carbon, or 4.8 times 10 to the negative 2. So it might be tempting to try and memorize that if you have grams and you want to go to moles, that you divide. Or that if you have moles and you want to go to grams, then you multiply by the molar mass. But I would encourage you to continue thinking about it like a unit analysis problem like this. Don't try and memorize this as a formula. Even though it is fairly formulaic, when it does get a little bit more complicated, it'll be, well, we'll say it's easier to make mistakes if you just try to memorize a formula. Because here we have the visual check that we have grams and we're dividing by grams. And so those can cancel out. So we can go through and do a very quick check that we've set things up correctly. Yeah?
We don't have another step that is asking the atoms?
Oh, sorry. You're right, we do have another step. Oh, well. So how do we go from moles to atoms? Yeah, so 1 mole equals 6.022 times 10 to the 23. So 1 mole on the bottom, 6.022 times 10 to the 23 atoms. So we can take our previous number and multiply it by 6.022 e to the 23. So that's going to equal 2.9 times 10 to the 22 atoms of carbon. Hmm?
Are we able to use notes?
No.
for the test?
No notes on the test.
Memorize that formula?
So memorize the 6.022 times 10 to the 23, yeah. That's the only one that you have to memorize, though, because the rest of them are on the periodic table. Any other questions? No. Right. You will have a periodic table for the test. All right. Now we're going to calculate the mass of 1.23 times 10 to the 24 helium atoms. So starting with 1.23 times 10 to the 24 atoms of helium. So our conversion factor from atoms to moles. We will need, so 1 mole on top. Well, that is for the molar mass. So that's moles to grams. So we're going to go from atoms here to moles. 6.022 times 10 to the 23. But then, yes, 1 mole equals 4.00. Thank you. Yeah, and then we'll have 1 mole here. 6.022 times 10 to the 23 atoms, helium. And then we can link multiple conversion factors together here. So we don't have to do any math or risk any rounding until the very end. And so now we'll use our, yeah, so we have 1 mole here. So how do we go from 1 mole to grams? Yeah, 1 mole on the bottom. Yep. And so now we multiply everything on the top and then divide by everything on the bottom. So this will be, actually, let me write this down first. So when you type it into your calculator, you can do it this way. And I'm going to include the ones here just to illustrate a point. You don't normally need to include them. But 1.23 times 10 to the 24 times 1 times 4.00260, and then divided by 6.022 times 10 to the 23 divided by 1. So when I say divide by everything on the bottom, literally hit divide before everything that's on the bottom. And you can type everything into your calculator like this, and because of order of operations, it'll go left to right, and it'll do everything in the correct order. So 1.23, 24. So this is going to be 8.17535. But with correct number of sig figs, it's going to be 8.18 grams of helium. Definitely when I give you calculator tips like this, test them out for yourself. Try them with parentheses, try them a bunch of different ways, and prove to yourself that you do get the same number. I still do that occasionally. I'm like, oh, can I type this calculation in with fewer button presses? Sometimes you can, sometimes you can't. Sometimes it's hard to tell which order of operations the calculator is going to use. Is there any other questions? Cool. Oh, I was actually wrong about the depth of the marbles, because if 22 pennies is 6.022 times 10 to the 23 copper atoms, if we had 6.022 times 10 to the 23 pennies, that would cover the Earth's entire surface to a depth of 300 meters. 300 meters deep of pennies. And that's, oops. It's also 6.022 times 10 to the 21 dollars, which is probably more money than has ever existed. And 1 crystal of granulated sugar has a mass of less than 1 milligram. Took 1 single grain of sugar, a diameter less than 0.1 millimeter. But 1 mole of sugar crystals would cover the entire state of Texas to several feet if you took those teeny, teeny, tiny grains of sugar. It's a lot of sweet tea. So for elements, our molar mass is the mass of 1 mole of atoms of that type of element. And this is where we start to make things a little bit more complicated, but not too much more complicated. If we have a compound, though, those compounds are made up of multiple elements. So the molar mass is the mass of 1 mole of molecules, or formula units if we're talking about ionic compounds. And so we can convert between the mass of a compound and the moles of a compound. We have to calculate the number of molecules, or the formula units, from moles. So this was the thing that we did actually at the very last in the very last section of the last chapter, where we calculated formula mass. Basically, you count up how many of each type of atom there is, multiply those by their molar mass, add all that together, and you get the total mass. So formula mass, again, is the sum of the atomic masses of all the atoms in a chemical formula. So for the formula mass of calcium nitrate, you're going to have, let's see. Oh yes, the formula mass and the molar mass are the same. So the formula mass of calcium nitrate, if we count up the number of atoms, we have calcium, nitrogen, and oxygen. Those are all the types of atoms that we have. So how many calcium atoms are there? Just 1. How many nitrogen atoms are there? 2. So because the NO3 is inside the parentheses and there's this 2 outside, it means 2 times everything that's inside the parentheses. So this is going to be 2 nitrogen atoms, and then how many oxygen atoms? 6. So again, it's inside the parentheses and there's a 2 outside. So multiply that by 2, there's 6 of those. And then we multiply the number of each type of atom by its molar mass from the periodic table. So for calcium, it's 40.078. For nitrogen, it's 14. What does this one have? 00674. You get that right? 674. And then for oxygen, it's going to be, oh, not 16, it's 15 on this one. 15.9994. For some of these, or for some different periodic tables, they round to different numbers of digits. So that's why you'll see slightly different numbers. Like for oxygen, it's usually rounded to 16.00. And so now we just multiply these. So this one's going to be 40.078. And then 14.00674 times 2 is going to be 28.01348. 6 times 15.9994. Or 6 times 15.9994 be 95.9964. And then we just add all of those together. So this is going to be 164.08788 grams per mole. Sorry, I got all the way under the edge there. So the formula mass is 164.08788 grams of calcium nitrate per mole of calcium nitrate. And the molar mass is the same. Yeah.
I think there was something about this in the last slide, but I didn't quite get it. If ionic compounds don't exist in discrete units, then how do you like count?
So you're counting the number of discrete units in the whole compound. So yeah, it ends up, if we treat ionic compounds like molecules and that we're counting the formula units, then the math is the same. So yeah, because salt is going to be something like a sodium. Let me do it this way, right? NaCl, NaCl. Right, and then that stacked on top of another layer that's alternating, stacked on top of another layer that's alternating. And so we're just looking at, we don't want to write out, oh, we have this one molecule or this one grain of salt, crystal of salt, and it's N 6.022 times 10 to the 23, or sorry, not N, but NaCl 6.022 times 10 to the 23. Yeah, we're just, it's a different way of counting them. Instead of saying, yeah, all of them, or each one, there's like 1 mole of each, we would just say 6.022 times 10 to the 23 NaCl. I'm going to zoom that. Formula units. Yeah.
Will the molar masses and the formula masses always be the same, or will
They'll always be the same.
intermediate?
No, they'll always be the same. So the formula mass is the atomic mass units. The molar mass is in grams per mole. And since those are numerically the same, then they end up being the same number all the time. Yeah. Any other questions? Okay, so if we want to find the number of moles in 22.5 grams of dry ice, start with our 22.5 grams. And dry ice is carbon dioxide. So whenever we're given a compound, your first step is always going to be to calculate the molar mass. So for this, we've got carbon, we have oxygen, and then we have 1 carbon atom, 2 oxygen atoms. And the mass of carbon, 12.011, and oxygen is going to be 15.9994. So this one's going to be 12.011. This is going to be 15.9994 times 2. 31.9988. And then we add those together. So it's going to be 44.0098. That's grams per mole CO2.
So you put that at the bottom and 1 mole at the top?
Mm-hmm. So this will be 44.0098 grams of CO2 is 1 mole of CO2. So writing this out down here as I have, where it's this grams and then there's a slash moles, is the same thing as the way I was writing it out before, where it was 44.0098 0.98 grams of CO2 equals 1 mole CO2, just more compact. So then it's 22.5 divided by 44.0098. It's going to be 0.511249, round that one up to 8 moles of CO2, and then 3 sig figs, 0.511. Cool. Unit conversions. So, just to like briefly recap where we're getting all these conversion factors from, right? If we have individual elements, they all come from the periodic table. If we have compounds, so more than one element, then we still go and we get the individual elements conversion factor, the molar mass from the periodic table, and then add them up so that we get the mass of the whole compound. Right? So it's going to be based on all of the elements that are in the compound. So we're just creating all of our conversion factors now, which I think in some ways makes it easier because you're given the compound name or formula, and then you know how to build that formula, that conversion factor between grams and moles. You don't have to memorize a table of values. Yeah.
Does it matter whether you write it in scientific notation or not?
For this one, it doesn't, because this correctly shows that we have 3 sig figs. You could write it in scientific notation. Cool. Any other questions? So this is going the other direction now. Actually, no, it's the same direction, huh? Yeah, same direction. So same thing here. We got calculate the number of moles of nitrogen dioxide in 1.18 grams of nitrogen dioxide. So 1.18 grams of nitrogen dioxide. So what is our first step? Because we're working with a compound. The molar mass of each one, which is the same number as the AMU. Yeah, the atomic mass. So, or you also need to know how many of each, right? So it's nitrogen, 1 nitrogen, 2 oxygen. Nitrogen is 14.00674. And oxygen is again 15.9994. So some of these are going to pop up a lot, right? You're going to see a lot of oxygen. You'll probably just end up memorizing that one without even trying. So 14.00674, 15.9994 times 2. So add those two together and you get 46.00554 grams per mole of NO2. And there is a way that you can sort of shorten this math in your calculator. But I'll let you play around with that one to figure it out. And then I'll tell you I actually told you about it last week on Wednesday, but if you figure it out, can save you some time. So now how do I plug this in? Yep, 1 mole on top. And 46.00554 grams of NO2 on the bottom. And you might want to take shortcuts here in writing out the units, but it's writing in the units that lets us quickly check that, oh yeah, grams of nitrogen, grams of nitrogen dioxide gives us the correct units. So 1.18 divided by 46.00554, and that's going to be 0.025649 moles nitrogen dioxide. And so we can still write this number with the correct number of sig figs without using scientific notation. So 0.0256 moles of NO2, but in scientific notation would be 2.56 times 10 to the negative 2.
Does it matter which one we write down, or which would be what you prefer for us?
So this, following the rule of thumb that I gave you before, it's less than 0.1. So you should write it in scientific notation.
Would we get dot points if we got?
Not at this point, no. If you can write the number down, and this is the thing with scientific notation, is that it's a tool, and there's sometimes where it's required, and there's sometimes when it's not. So I think primary significance of scientific notation is showing the correct number of sig figs. So for very small numbers, you don't always have to do it. But for large numbers, you almost always have to do scientific notation. Cool. Any other questions? All right, let's do, actually I think we got time for a couple more. So how many molecules, H2O molecules, are in a sample of water with a mass of 3.64 grams? Now notice here we're not looking for moles, we're looking for, wait, actually, no, this goes to 945. Never mind, we got plenty of time. How many H2O molecules are in a sample of water with mass of 3.64 grams, right? So we've got molecules here, not moles. But we're still going to start with 3.64 grams of water, which is H2O. And then how are we going to get from grams to molecules?
Gotta break down the compound to individual.
Uh-huh. And what is that going to help us do? So starting with grams, we'll go to moles.
Grams per mole.
Mm-hmm.
Then we can go from moles to atoms with the Avogadro's number.
Yeah, we can go from moles to, well, in this case, molecules. But correct, Avogadro's number. So we're going to have 2 hydrogens, 1 oxygen. Forgot a 9994. And then hydrogen is 794. So 1.00794 times 2, 2.01588, 15.9994. This is going to be 18.01528 grams per mole of water. And then the same thing that we've been doing. So 1 mole of water on top, 18.01528 grams of H2O on the bottom. Then how do we get from moles to molecules?
So 1 mole at the bottom,
Yeah, 1 mole at the bottom,
and then
6.022 times 10 to the 23 on the top. So you multiply everything on the top, 3.64 times 6.022 e to the 23, and then divide by everything on the bottom, so divide by 18.01528. So it's 1.2167 times 10 to the 23 molecules of H2O. So here we kind of changed up the units a little bit from what we were doing before, right? We were talked about going from moles to atoms, but because we have moles of a molecule instead, we go from moles of the molecule, or sorry, yeah, moles to molecules. How many hydrogen atoms, oh sorry, there were questions? Oh, sorry, I didn't do the sig figs yet because I'm going to ask another question. But you're right, yeah, 3 sig figs. Yeah. So if we have this many molecules of water, how many atoms of hydrogen are in that many molecules? So if I had 1 molecule of water, how many hydrogens would it have? 2 hydrogens. If I had 100 molecules of water, how many hydrogens would I have? 200. So if I have 1.22 times 10 to the 23 molecules of water, how many atoms of hydrogen do I have? It's just double. So there's 2 atoms of hydrogen for every 1 molecule of water. So this would be 2.44 times 10 to the 23 atoms of hydrogen. And then the atoms of oxygen here would be the same, right? Because there's only 1 atom of oxygen for every molecule of water. So that question is similar to asking this next question. If everybody's done with this slide. Oh. No, that was.
Oh, that's just an extra.
Yeah, that's, well, leading you into the next part. Yeah. So that's the same question as asking, how many leaves are on 14 clovers, assuming they're all just regular 3-leaf clovers? So if you have 14 clovers, how many leaves would you have? 3 times the number of clovers. Or if we wanted to set this up more formally to match the math that we've been doing up until now, we'd have 14 clovers. And then we know that there's, given on the right here, 1 clover at the bottom, 3 leaves on top. And I'm telling you, when you figure out that you can apply unit analysis to like literally everything, unlock some fun math, some actually fun math. Because you can calculate silly things like, if I counted 5 atoms per second for every day for every second of my life, right, how many atoms would that be? Or how many times does it take to slap a chicken to cook it? Right? That's all just unit conversions. It's unit analysis. Yeah, it's great for grocery shopping. If you're trying to compare like milk prices, but one's like, a quart versus a gallon, or not a quart, but like a half gallon versus a full gallon, right? How many gallons per dollar are you getting, or dollars per gallon?
Can I do that on my weight? My weight times my weight to find out how many atoms I have inside of me?
Yes. We can do that. We can do that. We'll do that in lab on Wednesday if you bring it up again. But I'll do it for my weight.
Are we gonna make diamonds in lab too?
No, we won't be making diamonds in lab, unfortunately.
I want to have another diamond.
We gotta pay for all the chemicals somehow. Okay, so in 14 clovers, there would be 42 leaves. So 42 leaves. So same idea, right? We have one molecule of water, to get us back on track. There are 2 hydrogen atoms, or 1 oxygen atom, or we can use the chemical formula to figure out how many of each type of atom there are, and we could calculate for each of those individual atoms how many there are in a whole bunch of atoms. This, applies to a lot of things, like how many legs are there on one spider, or how many legs there are on a chair. And actually, oh no, that was the, well, you guys familiar with the argument between, like, are there more wheels or doors in the world? Right? You start thinking about, it's like, okay, well, every car has 4 wheels, but then a lot of cars have 4 doors. And so what you're kind of doing is you're doing this, but kind of intuitively, like, if there are more things that have more doors than wheels, then that would mean that there's more wheels or doors. We won't go too far into that. But right, it comes down to that fact, though, is that we can count, like, if there's 1,000 cars, and they all have 4 wheels, that's 4,000 wheels. But if only some of them have 2 doors, then there's less doors than wheels. But then you got to talk about motorcycles, which have all wheels and no doors. And I have a unicycle. So the idea, though, that like we can talk about these things in proportions, that we understand that, applies to these molecules as well. And it can help to have a mental image of the molecule, like water, right? You look at a car and you can see 4 wheels. You can't really look at a water molecule, but you can have this symbolic representation, right? So there's 2 hydrogen atoms for the one water molecule. So the relationships inherent in a chemical formula allow us to convert between moles of the compound and moles of a constituent element. So now we're starting to get back towards how many potato chips can we eat? How much sodium chloride, how much table salt can we eat and stay below the FDA recommended limit? For some other ones here, right, carbon dioxide means that there's 2 oxygen atoms for every 1 CO2 molecule. So there will also be 2 dozen oxygen atoms for every 1 dozen CO2 molecules. Or we could even go so far as 2 moles of oxygen per 1 mole of CO2. And so really what we're doing is we're looking at the formula and seeing that there's 2 oxygen atoms in every CO2 molecule. So if we have 1 mole of molecules multiplied by 2, gives you the number of oxygen atoms, or moles of oxygen. So if we have 18 moles of CO2, how many moles of oxygen do we have? Well, 36 total, 2 per CO2 molecule. And just to write this out more formally, right, so for 1 mole of CO2, that's 2 moles of oxygen. So down here would be 1 mole CO2, 2 moles of oxygen, 36 moles of oxygen. Mm-hmm. I'm telling you, a lot of chemistry is not like super hard concepts, but it's a pile of easy concepts. Right? The silhouette of chemistry is scary because it's this huge pile. But when you start digging through it, there's a lot of individual pieces. So if you can treat any chemistry problem as a set of individual pieces, it's a lot easier to tackle. So how about the number of oxygen, or the number of moles of oxygen in 1.4 moles? Mm-hmm. And again, I'm just going to take the time to write this out a little bit more formally so that we'll have it on the slide. But because there's, well, for 1 mole of, and what is the name of this compound? Not hydrogen sulfide. What is, it starts with an H.
Hydro,
So it's, well, what kind of compound is it? Starts with an H. It's an acid. And it's hydrogen, and then it's more than one type, more than one other nonmetal. Sulfate.
Wait, can I get it right?
Almost, you got part of it.
Persulfate, because it's weird.
IT, so it changes to OUS.
It's ATE.
OAT, so ic,
Yeah, so if that's sulfate, then it's sulfuric
then oxy acid.
acid. Sorry, 1 mole of sulfuric acid is going to be 4 moles of oxygen. So 1 mole of H2SO4 is 4 moles of oxygen. So yeah, we just take 1.4 and we multiply it by 4. So it's going to be 5.6 moles of oxygen. Yeah.
I think this is slightly irrelevant. Why is it sulfuric acid, not sulfic acid?
That just comes down to some like conventions in naming. Like if you wrote sulfic acid, probably wouldn't mark that wrong. I'd like write down the correction for you, but I don't know if there are specific rules for like why it's sulfuric and not sulfic acid. You develop an intuition for that kind of thing. It's kind of like dropping if there's 2 vowels for molecular compounds, like if it's monoxide, we drop one of the O's. Yeah, sometimes it's just,
Like a grammatical thing.
yeah.
Does the number of hydrogens change the name, or it doesn't matter?
The number of hydrogens does not change the name. No, it doesn't matter how many hydrogens there are. Well, if there's 1 hydrogen versus 2, so if it's not completely balanced, then it would be something else, but we're not talking about those. Don't address those in this class, I should say. Cool. Any other questions? Perfect. So when we come back, maybe we can answer this question right now, actually. 4 minutes left. I'm tempted to go over more nomenclature now. No? Okay.
What was the question?
Go over more nomenclature. Because we could do this problem, but like nomenclature is on the exam on Wednesday, and I want to make sure that you guys are good on nomenclature.
I was just gonna say, you better get your curve ready, 'cause
Okay, so let me, wait, how do I add this? I want to add a page. Okay. So what kind of compound is this? Oh, what kind? Acid. Acid. Because it starts with a hydrogen, so it's an acid. What type of acid is it? 2 types of acids. Binary acid, yeah, because there's just 2 compounds here. And there's no oxygen, yes. So it's a binary acid. So every binary acid starts with the same thing, and that is hydrosulfic acid. So changing the ending there to IC. Or it could be hydrosulfuric acid.
the ATE ending changes to IC.
Yes.
And what was the other one? The OUS?
ITE changes to OUS. So if we had what type of compound is this? Ionic, molecular, or acid? Acid. And what kind of acid? Oxyacid. There's more than 2 things, so it can't be a binary acid. It's an oxyacid. And then the base form of NO2, how many oxygens does the base form of NO2 have? Was it 3? It's 3. I think I heard somebody say 3. The base form of the oxy acid formed from nitrogen is nitrate, which is NO3 minus, so that's nitrate. And then our compound only has 2 oxygens. So it's nitrite. So NO2 minus is nitrite. So we have an oxy acid. So we change the ending, and here ITE changes to OUS. So this would be nitrous acid. Cool. That's the rule for oxyacids. So ITE changes to OUS. This is ITE, and then ATE changes to IC. All right, now we're pretty much out of time. So.